thank you everyone for joining in. Today, Professor Brian from University of Washington will be giving a brief talk on virtual oscillator controllers for power systems. So please put your questions in the chat, and once in a while when Professor sees the questions, he will answer. So go ahead, Brian, please go ahead, you can start.
All right, well, thanks for the invitation, and yeah, this is really great to have this audience across the world. I've actually been building a good research collaborations with people from your area. Have a couple researchers, actually a few in my lab from IISc, and anyway, I have a lot of respect for the research going on over there in Bangalore and really great schools there. Okay, so today I'm going to talk about, let me go in full screen mode here and swap my screens. Okay, all right, so today I'm going to be giving an overview of some of this work I've been doing on this, this approach that I call virtual oscillator control. And I decided to broaden the scope slightly. At first, I was just going to talk about AC systems, but this talk today will actually cover both DC and AC systems. And really the key idea here is we're trying to engineer power converters and their controls so that we can have a single building block. And then to build larger systems, we can take just multiple copies of this building block to create large systems with no explicit communication channels. Kirchhoff's laws do all the talking for us, so to speak. Okay, just a brief acknowledgement of all of the great collaborators who've helped me along the way on this topic. And okay, this is just super basic and simple. Everyone here is I'm sure way ahead the curve on these things, but there's two basic facts that we're going to be using to design and analyze the behavior of this type of control, and for the remainder of the talk. The first point here is related to especially pertinent for DC to DC systems, and we'll talk about that later. And the idea here is that any switching converter is going to have some amount of ripple, and this is just intrinsic, unavoidable. You can't get rid of it. And the second one is that we always need controls of some sort. You know, power converters by themselves are incapable of precisely regulating things, and the way that I prefer to do things is generally with digital control, because we have a lot of algorithmic flexibility to program whatever behavior we're looking for. Okay, the other aspect I was hinting at in the title slide is that we're seeking modularity. Here, modularity is highly beneficial for several reasons. One of which is just simpler installation. You can just kind of piece things together like you have a bunch of puzzle pieces and build something larger. Second is expandability. So if you decide later that you want to add more to your system, you can do that in a piecemeal fashion. Resilience to failures, if you design things properly, is another key benefit. And depending on how you design things and the properties of the converters, you can also enhance efficiency, but that all depends on how you design things. So here's just a couple examples of modular power electronic systems. Oh, looks like there's some blue mark on my screen. I don't know what that is. Well, anyway, so there's some.
Just one second. Vishal, just disable annotation by participants. So just disable that. Yeah.
All right.
Yeah, go ahead, Brian. Yeah, go ahead. Go ahead.
Sure. Okay, so I guess there's some objectives that we're looking to do when we have the multi-converter systems. In the AC system case, it's really has to do with synchronization, or at least that's one of the key objectives. It's a prerequisite for having any functional AC power system. You need to have waveforms synchronized. This is both true with machines as well as power converters. And so this is just the very simple and broad objective that we refer to simply as just synchronization. There's many objectives you can be chasing for DC to DC converters, but the one that we're going to be focusing in on is something called interleaving. And this is just an approach we're going to use to get ripple cancellation. And I think many in the audience are familiar with the concept, but the idea is that if you have some inherent unavoidable switching ripple that's coming out of many power converters, you can actually stagger the timing or interleave them so that the timing instances of the switch instant is spread out over time. And whenever these interspersed ripple waveforms combine together due to Kirchhoff's law, we get some sort of natural cancellation effect. It's a really nice idea. And in the controls world, in people who work on nonlinear dynamical systems, this is oftentimes called splay. So if you're curious and you go into the more of the mathematical literature, you might see this word come around. In the power electronics world, we usually call this interleaving. Okay, so let's just put these two things side by side. When you look at them, they appear very opposite in nature. In one case, we want to align waveforms so that they're on top of each other. And then in the interleaving case, we want everything to be pushed away equally from each other. So it really looks like we have two complete opposite things we're trying to achieve. And this is really why this concept I'm about to describe is interesting, or at least I think it's interesting. What we're going to show is that you can actually achieve both of these objectives for different systems. You don't do this in the same system, although in theory that might be possible if you're clever enough. But we can actually achieve synchronization or interleaving with the same exact controller. The only difference is that you just have to introduce a sign flip on the feedback. So you have, I guess, what you could call negative or positive feedback in one system or the other. And if you flip that sign, you'll get synchronization. And if you flip the sign the other way, you'll get interleaving. And this power converter can be, this is a generic diagram here. So for the AC waveform synchronization, this will be an inverter. And for the DC to DC case, this will be a DC to DC converter. Okay, so here's just the rest of my talk. I have to stay fueled on coffee here. It is Seattle and it is very early in the morning for me. So you'll have to bear with me as I take my periodic drinks of coffee. All right, so here's the way we're gonna do the rest of the talk. What I'm gonna do first is I'm going to focus on experiments, and I'm not going to show any math to begin with. I'm just going to show measurements, waveforms, things that we've actually built and done in the lab. And hopefully that gets you into this idea that what this bold statement I made, that it is true and you can do it physically. But for all the curious minds in the audience, you will be wondering, well, how does this work? What is the underlying mechanism that allows you to recycle the same controller and get interleaving or synchronization? How does that work? And that's the second part of the talk. We'll look at the mathematics. And then once we have a mathematical model, we'll analyze the stability of these various operating conditions. Okay, so we're gonna jump into some experiments here, things we've built. And we're gonna first look at the AC systems where we wanna synchronize their fundamental component. So I believe in India that'd be 50 hertz. Over here in the US would be 60 hertz. Either way, we're just going to call it omega star. And okay, so let me take a minute here to I guess give a high level idea of how this virtual oscillator controller works. This is a nice diagram to explain the main idea. The main idea here is that we have our power converter. This moves energy from point A to point B. And strapped around the power converter is a digital control loop. And that's everything that is pictorially drawn in this blue box. So everything in this blue box is just code and the functionality of, let's say, a DSP or a microcontroller, possibly an FPGA. So even though I've drawn this, the interior of this blue box is as if it's a circuit where I drew resistors, inductors, capacitors. In reality, this is nothing more than code. So this is why we call it a virtual oscillator controller. What we're going to do is we're going to program the dynamics of this nonlinear oscillator circuit. So this circuit, as I've drawn it, does have a set of differential equations that govern its dynamics. All we do is we discretize that and then write those discretized differential equations inside the digital controller. And hence it's virtual. It doesn't physically exist. You can't hold this inductor in your hand. It's just nothing more than a number and a line of code. Okay, now this structure, I call it an oscillator because it indeed does exhibit resonance. So this LC tank does have a resonant frequency. And there are many intricacies I don't have time to discuss here on how you pick this conductance, which I denote as sigma of this, this element here, the precise values of this nonlinearity. So this is a cubic nonlinearity with some coefficient. How do you pick this, this value here? There's some gains. We're going to kind of sweep all that under the rug. The only thing I want you to remember is that the resonant frequency of the LC tank and the sign of the feedback, those are the only two things you have to really keep focus on for the rest of the talk. Okay, so here we have the system. We have a physical current that is coming out of the power electronics. It's digitized through an analog to digital converter. It is essentially extracted from the oscillator because we do have a negative sign here. So it's actually extracted from it. The voltage that envelops across our circuit we're emulating is then used to synthesize a voltage command. And due to pulse width modulation, the average or the switch cycle average value of the true physical voltage, which I call V tilde, should track V. So it's a way of just making this circuit, if you look into the switch terminals, behave like this oscillator. Okay, now just use that knowledge there to now take a copy of that where we have multiple copies of that. So you have multiple DC to AC power converters. You connect them in parallel. This could be a microgrid. It could even be a large power system. That's actually another aspect of my research I've been working on, is how do you take this type of controller, not only use it in microgrids, much like you would with Droop controller, but use it on large scale AC systems. But please, yes.
Brian, one question. How is this different from loop system?
It is very similar to that idea of hardware in the loop. The main difference, though, is that this is the controller itself for the power hardware. Usually with hardware in the loop, you're trying to emulate something that you might not have. But yeah, that's a great question. It is very similar in spirit.
Okay, thank you.
Okay, so here's an AC power system. For simplicity, let's just discard the idea of a large power system. This is just a small microgrid, 3 power converters directly in parallel across a single load that they share. And again, there's no explicit communication. These are 3 independent digital controllers, 3 independent power converters. And the way these things function with each other is the fact that Kirchhoff's laws allows them to interact. And so here is an experiment where we have 3 inverters with the virtual oscillator controller. And here I've been a little different. I actually have programmed, well, actually, let me see. There's 2 aspects on this 3rd power converter. First is that physically its power rating is half of the first 2. And then what we do is we can introduce, there's actually scalings inside the controller. This is one of these details we don't have time to jump into, but the parameters, the scalings in them, you can actually, in the code, tell each converter what its power rating is. And when you connect them in a system, they will intrinsically share proportionally by power rating. That's a very nice idea. This is something that machines do on the power grid, for instance. And here is a cold start. So they're turned off, randomized, we turn them on. They do this little dance together, and then they synchronize, and indeed, the third one is producing 50% of the power of the other two. So this is how, showing you how they synchronize and pull together, and it's due to the feedback in combination with Kirchhoff's laws, which is the physics. And then here is just showing their response during a load step. So you can see we have a very rapid response.
Hey, Brian.
Okay, so here, yeah, please.
So what happens to the currents during the startup when they are not synchronized?
Oh, actually here they are not synchronized.
Okay.
Yeah.
Oh, these are okay.
Absolutely,
Understood.
yeah.
Okay.
So, yeah. So in this experiment, just make sure we're all on the same page. We actually initialized in this experiment. They had randomized initial conditions at startup. So this is why they're all kind of oscillating against each other. Okay, so here's another experiment where resistive and linear loads are kind of ideal. Many loads that we have to contend with in the real world are nonlinear. And so here's just an experiment we ran with diode rectifier load just to show the behavior. And indeed, these power converters, they regulate a fairly clean sinusoidal waveform, and the load just takes whatever current it wants. So it's, in this case, this load is obviously pulling in these pulsating currents, and the power converters gladly oblige. And this one, all three of these are equal power ratings. So you can see they have equal magnitudes. And then here is loads. Oh, actually, here is an experiment where suppose converter number 3 fails for some reason. The other two pick up the slack and sustain the voltage magnitude. And suppose somebody takes converter number 3 and they fix it and they put it back on the system and they start it up. And you can see it resynchronizes. So as you're looking at this, yeah, go ahead.
Just one very quick question. Where is the voltage reference signal in your schematic? I mean, it is tracking some voltage across the load, right?
Yeah, so the answer to that is that there is no explicit voltage reference. If you look at this, there is no ref feeding into it.
Yeah.
It actually is hidden behind the scenes. So the way you compute this alpha, L, C, and sigma is, okay, actually here's exactly how we do it. We everything in this gray box, we first design it so that when it is isolated and open circuited by itself, it produces exactly an amplitude of 1 volt RMS. And then we produce this scaling here so that when the full nameplate rated current is coming out of the power converter, this current here is 1 amp RMS. So it's essentially like a per unitization. And then this voltage scaling will be equal to the voltage nameplate power rating. So it takes a voltage of 1 volt and scales it up to however many volts you need. And then the stiffness of the system is dictated by how you pick all these parameters. Okay, so hopefully that gives you all a flavor of how we do the design of this. And there's papers I can share with people. You can email me and I can send you those. Okay, so for those of you in the audience who work on microgrids, the standard way to do this stuff is with droop control. Droop control has been around since early 90s, and it's just countless papers related to droop control. And so you might be wondering what the difference is. And it turns out that although this virtual oscillator looks wildly different, it looks like this strange animal you've never seen before. If you take its dynamics you average them over an AC cycle, in this case a 50 or 60 hertz AC cycle, and you look at the steady state frequency and voltage with respect to real and reactive power, it turns out this oscillator has droop laws naturally built into it. So in a way, it is like a droop controller. So you might be thinking at first, well, then why would you use this over droop control if they are functionally the same? The reason why is because you have to realize just nuance in my statement. They are identical only in steady state. In the time domain, they're very different. The oscillator controller is what I refer to as a time domain controller. There's no concept of a phasor. We don't need to do averaging or filtering. This feedback is literally acting on the instantaneous current. So if something happens, it reacts instantly to it. If you're familiar with droop control, you always have low pass filters, averaging, things like that to get rid of pulsations, harmonics, noise. And that makes the oscillator much more nimble and fast. So here is an experiment where we have the third converter turned off, which is this kind of a bluish waveform. There's a little bit of current circulating in and out of the outer branch capacitor. And when we turn it on, you can see that with oscillator control, it synchronizes in a couple cycles or a few cycles, whereas droop control, we get this kind of underdamped response and it's pretty slow. Okay, so hopefully that, you're probably wondering that as you're looking at these waveforms. Okay, now we're going to switch gears a little bit and go to DC to DC converter systems. And we're going to look at this interleaving splay configuration. Okay, so now that I've given you an idea of how this is done on DC to AC systems, it's pretty much the same idea for DC to DC. Okay, so this is actually a system I've been looking at, which is just a multi-phase buck converter system. So namely just a collection of buck converters that are all in parallel with one another across a common load. This would be very similar to something you would see in a computational system, where this might be representative of like a CPU or some sort of computational load. And in this case, this is where interleaving is used quite a bit to ensure that we have high quality current waveform going into the load. And again, like I said, there's only two things to remember, is the resonant frequency of this circuit. Instead of picking that to be a fundamental waveform like we did for the AC system, such a concept doesn't exist in DC to DC, so we actually pick it to coincide with the switching frequency. And the feedback sign is now going to take on a positive value, whereas earlier took on a negative value. And the way this works is this block here, there's nothing new here where this is droop. This is actually just conventional droop in DC to DC systems. So there might be some of you who are used to droop being only for AC systems. It turns out that the droop is also used in DC systems. It's basically just like a resistive drop emulation. Same idea. This is used quite a bit in multi-phase buck converter systems. So all this is old stuff. There's nothing new here. And the new part is just the fact that we feed the current information to this virtual oscillator. We use the signals that are being emulated, and then we use that to synthesize the carrier waveform that is going to the PWM. So what's actually happening here is the virtual oscillator in this case is actually creating the timing of the triangular carrier waveform that is used in the PWM, which is why the resonant frequency of it is now tuned to the switching frequency.
So one very quick question. So
Sure.
the current will be sampled at switching frequency because, or you have to sample it at a higher frequency?
Yeah, and this implementation I'm showing here, we have to have a fairly high sample rate. So suppose you're switching at one particular switching frequency, you need to be able to measure that waveform and its ripple content. So you would probably have to sample, let's say, 10 times faster than that.
Okay. Okay.
And
Okay.
those of you familiar with digital control and high frequency power converters would instantly recognize that that's problematic.
Yeah.
Maybe a limiting issue. Now, what I'm pleased to say is that we have research that's going on right now. It's unpublished, and we have solved that problem. Oh, actually, we do have one paper we published last year at ComPEL, where we do have a sample and hold approach where you only have to grab one sample each switch cycle. So we have resolved that, but that's beyond the scope of this presentation. Okay.
Thank you. Thank you.
Okay. Thanks. Thanks.
Mm-hmm. Of course. Okay, so let's go to the experimental setup. This is just the diagram. So here is a multi-phase buck converter system, 5 power converters. Oh, actually, let me tell a little story here. The first paper that was maybe written 3 years ago on this concept, where we had this approach, we were at a conference, and we had this grad student who was out there presenting this, and immediately people in the audience said, "Oh my gosh, I won't believe this until I see it in hardware." They could not believe that this idea would work. Now, one of the things about me is one of my favorite things in life is to prove people wrong. When someone says something is impossible, I really like showing them that it is possible. So anyway, we were emboldened after that conference. We said, "Oh man, all these guys said that this is not going to work." So we went ahead and built it. And in fact, one of the people in the audience who is a really highly respected, really famous person in the power electronics world said, "Hey, this simulation right here neglects the fact that you might have asymmetries in a DC to DC converter. You might have a bus bar, and the load might not be located symmetrically in the middle, and there might be there's additional resistances here that ensure that the first unit is maybe farther away electrically from the middle point." And he had a good point. So we said, okay, we're going to build an experiment that actually has this kind of configuration. So we purposefully added parasitic resistances and built the system. This experiment uses an FPGA to do this approach. It's just reading in the current sensor value, and this particular version had this kind of brute force oversampling approach. Okay, so what we're going to look at here is the waveform. So at a switching time scale. So here, much like the AC waveform case, they're randomized to start with. None of the units have any clue the timing of the others. So this is just randomized switching in figure A when we start up. This is a zoom in of this point here. This is the total load current. These are the individual currents. And I think it's within, let me see here, a few tens of milliseconds here. You can see they indeed push each other apart. So 1/5 of an AC cycle, or of 1/5 of 360 degrees is around 72 degrees. So they interleave and push each other away. And if you were to add and remove units, same thing can happen. So suppose that we start out with 4 units, and maybe the 5th converter wasn't working for some reason. We repair the 5th converter and turn it on. Then eventually they will indeed push each other away. Okay, so that's, I guess I'll just mention that prior to this, this approach for DC to DC systems, all prior approaches were at best distributed, mostly centralized. In fact, I think this paper that describes a distributed approach, it's been around for quite a while. it turns out that if you go to industry and see what they're using, they pretty much only use a centralized approach. There's usually one IC that takes care of the timing, and this takes care of something called phase shedding, which is used in multi-phase buck converter systems. So our approach is fully decentralized and scalable.
So Brian, in distributed, do you have multiple ICs?
Yeah, the distributed approach is interesting. You actually have you do have multiple converters, each with their own controller, but they do have to talk to each other and share information across a communication bus.
Okay, got it.
Mm-hmm. Whereas for our case, the way they talk to each other is through the intrinsic physics, and that's actually where the mathematical modeling will come in next.
Okay, got it.
Okay, so now that I got all the hardware people excited in the audience, all the math people, you might be wondering if I'm going to leave you behind, but don't worry, I haven't forgotten about you. We're going to look at some math. All right, so here's the mathematics. If you forget about the intricacies that make the DC to DC and the DC to AC system distinct and different from one another, the common kernel that is true and identical to both of them is this virtual oscillator system. We can write down its dynamics like this. So this is just defining two states. One of them is a scaled, one of them is a scaled capacitor voltage, which I'll call Y. One of them is a scaled inductor current, which I'll call X. So namely this current and this voltage. This scaling value is actually the characteristic impedance of this LC tank. And you can write the dynamical system like this. And this thing, if it's isolated and this current is 0, this thing has a globally attractive, unique, stable limit cycle. You can prove this using something called Leonard's theorem, which is something that's well known in the nonlinear systems literature. Okay, now we're going to introduce network coupling. Now, again, what we're trying to do is in this talk.
Hi. How are you?
Oh, yeah. Yes, please. What's your question?
We shall just mute. Yeah.
Oh.
Yeah, go ahead, Brian. Yeah.
All right. Okay, so what we're trying to do here is we're trying to create a model that captures the salient and important characteristics of both the DC to DC system and DC to AC system. And this model will brush away some details that make them different, but we want to just zero in on what makes them the same. And what makes them the same is network coupling and feedback. So in both systems, it is true that the signal of this oscillator is dictating the timing of something. In the AC system, this is the fundamental AC waveform. In the DC to DC case, this would be the timing of the fundamental of the switching component and its timing. We have some feedback. We have this sign flip that we need to contend with. This can be positive or negative. And then we assume there's RL branches throughout the system and that they have identical R over L ratios. This is just kind of something we have to do for some mathematical convenience. In a practical system, it's not that important. You can write this in vector form where I is the vector of all the currents and this matrix Y is a Laplacian of the system. Okay, now we're gonna dig in a little bit more here. So we're gonna define things in terms of angles because the whole point of this discussion is we're trying to understand when angles synchronize and when angles interleave and push each other away. So we have to define an angle in some sort of way. And the way we do that is actually just based on the fact that we have orthogonal signals that live inside the controller, namely this state variable, the current and the voltage. They're orthogonal to one another, at least in steady state. And so we can use those to define an angle. So if you take the arctangent of that, that gives you an angle. Now, one thing we're going to do is we're going to subtract off the nominal angle that is rotating with this kind of nominal speed here. So this theta actually is kind of, you can say, an offset with respect to something that is spinning at the synchronous speed, where this could be the switching frequency or the grid frequency, it doesn't matter. And then this thing also has some radius too. So it's like an amplitude of the oscillation, and it's just a Euclidean norm. Okay, so now we have the idea that there's not only just one of these, there's n of them. So we just have to index these. And it turns out that Kirchhoff's laws give us these equations. It looks a little bit messy, but it's just trigonometry. So you can imagine that if we look at this system, we have voltages and currents. You can do all of Kirchhoff's laws. You can solve for the voltages and currents. Once you have the voltages and currents, you can plug them into this equation for the angle, this equation for the amplitude, and you'll get these differential equations, okay? Because we have differential equations for the inductor current and differential equations for the capacitor voltage, and they are identical to this one. You must trust me. There's a bunch of trigonometric tricks, but it's not too bad. It's just dealing with all the algebra. Okay, so this equation on the bottom is fairly difficult to deal with if you're looking at it. It's nonlinear, and there's these fairly high order terms, and it turns out that much of them don't really do much in terms of the dynamics. So we're gonna average out the dynamics of this system down here on the bottom over one full AC cycle, or one rotation. In the case of the grid, you can think of this as the fundamental. For the DC to DC, this is the switch cycle. And the switch cycle variables all denote with this, this bar variables, okay? And now when you average out this differential equation, these two differential equations, basically you just integrate them from 0 to 2 pi and then divide by 2 pi. You'll end up with something like this. And this equation looks just much more beautiful, I think. It's much simpler, it's cleaner. It gets rid of a lot of these higher order terms that, or some of these higher order terms aren't really doing much. And we get the network coupling. Remember, there's a Laplacian matrix that captures how all of these interact in a network. So we obtain that too. So you can see the network coming into play. And we're also going to denote angle differences with this theta jk. It just keeps things a little bit cleaner. Okay, so there's a few different configurations that are important to us. One of them is when all the angles synchronize, and that's kind of this first one here on the left-hand side. There's another condition called phase balancing, where if you think of all of these angles on a complex plane, it's just like if this thing had a center of mass where this thing has a balanced center of mass that's right in the middle of the system. These angles might not be equal between them, but there is a symmetry to the overall structure. You could bisect this in one way or the other and get some sort of symmetry. And then the most beautiful one, the one we care about the most, is the perfect interleaved case, which is actually a special case of the phase balance. That's where the angles are exactly all interspersed evenly. Okay, so here's the last part of the talk. And this is about stability analysis. So what we're going to do is we're going to actually go back to this model. This is the one I just showed a couple slides back. And we're going to analyze the stability of that system in the two angle configurations, one of which is the synchronized state. And then lastly, we'll look at the phase balance state. All right, so let's look at the synchronized state, which means that each of these angles, theta k and theta L, are exactly identical for any indices. And this is what you end up with. Okay, so this is not too bad. We'll just work through it quickly. This first statement is just restating the equation. I haven't done anything new here. So we have N oscillators. They abide by these average diff EQs. These are the same ones I just showed you a few slides back. Nothing new. Now, if this coupling gain is negative, then the phase synchronized equilibria is defined by these two configurations. So you search for what the equilibrium is, and this is what you find. They all must have this amplitude, as I'm showing here, and all of the angle differences must collapse to 0. And they're locally exponentially stable. And this local exponential stability can be ascertained by looking at the linearized dynamics of this system. This is actually the Jacobian matrix that you end up with. We have a nice diagonal structure, and it's pretty straightforward that if you look at the structure of this matrix Y, that is indeed a stable point. Okay, so this establishes that if all the angles are on top of each other, that point is stable. Okay, with this sign with negative feedback here. Okay. Now we're going to go to the phase balance case where everyone is pushed away, and now we're going to analyze the stability where all of these angles are spread apart. Okay, so here's the second theorem. Same thing, nothing new here. This is just same diff EQs from 4 slides ago. But now what we're saying is that if the feedback is positive, we also have a condition here on this conductance that's in the circuit. Then the phase balance equilibria happens when all of these complex numbers sum to 0, which actually this is the definition of this phase balance condition, and they have equal radii. And this thing is also locally exponentially stable. So in this case, we get a Jacobian that looks something like this. And these are these block entries here. So this one is a little bit more intricate, but if you parse out all of the structure inside the Jacobian, you can once again show that this thing is stable for positive feedback with all the angles interspersed. So I want to put a nice, neat little bow on top of all this so we can just look back and see the big picture. So this is the one slide that does it, okay? So if you work through all the math, there's 2, I could call them corollaries or whatever. There's 2 cases I didn't show here. But if you look at the synchronized case where all the angles collapse to be the same, and you have negative feedback, this was the first theorem. For the interleaved case with positive feedback, here's the second theorem, shows a stable case. And then there's also the, I guess you can say the opposite configurations. Those are unstable. And so indeed, this shows you that there is this kind of behavior that I've been hinting at through this entire presentation.
Brian, in the previous slide, in the Jacobian, what was JD? Yeah,
Okay.
JD.
Yes, yes. Okay, so this whole thing is J. And JD just happens to be this bottom right block entry. And if you parse out each and every, this thing is a matrix itself, then you can index the j-kth entry in this submatrix according to this expression.
Yeah, there's a question in the chat. Yeah.
Mm-hmm. Yeah, so the question says, why are we interested in angle instead of frequency synchronization in the theoretical part? Yeah, so that's a good question. I think for the synchronization part, indeed, you could have looked at frequency synchronization. Now, I'm also looking at a very special case here in this work where we have a symmetric network structure which means that the symmetry of configuration, there is actually that is a meaningful operating point to have them exactly phase synchronized as well as frequency synchronized. In a more generic topology where you can have line impedances, it could be a generic mesh or a structure or any structure. In that case, you might have phase offsets, and you'll probably have to look at frequency synchronization in that case, which is more general. Okay, any other questions?
Two quick questions. One is that see the oscillator has two states, which you have done the capacitor voltage and inductor current, and you have done some transformation, right, to take care of that. But the thing is the other, sorry, but these other filters, right, all these L and C's, those dynamics didn't come. I think they came like a phasor impedance, right? So those states didn't appear. So is it like there is a time scale difference between the oscillator and the impedances? Right.
Yeah, so for this generic model that is looking at the overall system, we just assume that there is RL impedances in the network.
Correct.
And we do actually retain the dynamics of those. So those are actually maintained in the remainder of the analysis. Now, one thing that we did sweep under the rug is there's some difference that we have extracted away from the DC to DC and DC to AC case. For instance, if you look at the DC to AC case, we have this more complex structure of the filter. So we indeed ignore that for kind of the sake of having a common model for both the DC and AC case. So yeah, there are approximations in this model, and I guess the objective here is we just wanted something that had a commonality of the key pieces.
So another quick question is that you see the. I'm sorry, my son is shouting.
Yeah, no,
I'm sorry. Okay, I'll ask this question.
Prof, put it in the chat. Put it in the chat. Yeah, go ahead, Brad. Thank you. Please go ahead.
Yeah, no worries, guys. I mean, I know what it's like. I have a loud kid in the house too, so don't worry about it.
Okay, thanks. Yeah, please go ahead. Sorry.
I don't know if there was another question.
Okay, I have one more question then. See, the thing is that the amplitude of the sine wave, right, that the voltage at the load port, that is coming from setting up the KV, right, the gain KV in the diagram, right?
Yeah.
So it is more like an open loop thing, right? Like, you put some KV, you do some calculations believing the values of the parameters of your system, but actually in practice, it will slightly differ, right? And instead of setting exactly, say, 120 volts, it will little bit change based on your the sensor gains and all that. So is that right?
That's somewhat right. Or yeah, mostly that is true. What we're doing is we're kind of at the design stage. We're picking the parameters of the system such that we get the desired voltage, not only in open circuit conditions. There's some subtleties too. You actually want the amplitude to stay within some range from zero load to full load.
Right.
This is just like if you have a droop controlled system, full reactive power to no reactive power, you need to have some range of amplitudes. So that's done at the design stage. And then once you have that, the intrinsic dynamics of the system have that. In fact, what I have kind of a little backup slide, because I think there's a lot of interest I've felt from people on the the AC and power systems case. And I did want to show this off a little. This is the most recent and most advanced version of this control type for DC to AC systems. You can see it looks very similar to what we had before. There's some additional differences that we have. The nonlinearity is a little more complex that we've zeroed in on. We now have ability to act on power set points. And this is the more complete picture of how this works. And actually, to shed a little bit more light on your question, all the parameters in this system, much like the simpler one I showed in my slides, here are the droop laws that you can actually build into this thing. 9-stage, you can get frequency and voltage droop. And these things are completely tunable at the outset. And these P and Q star commands can be used to bias your curve up and down, just like you would with an electric machine, a synchronous machine in a power grid, or with droop control.
I see.
So this is the most recent version we've been working with.
Cool. Thanks.
Hey, Brian, there are a couple of questions.
Okay,
From
can
the
we
audience?
implement, yeah, so from Pankaj, can we implement additional features such as inner current control, current limiting, output impedance shaping while ensuring synchronization simultaneously? Yeah, totally. So what you could do in this case is this version or implementation I'm even showing on this slide, which is the kind of newest, most advanced version of this controller, is this V alpha and V beta actually give you what is the AC waveforms here at the switch terminals. But suppose you actually wanted that voltage that I'm showing here to appear on your capacitors. Well, to do that, the proper way to do it is you would have to think of these as being a voltage command, where you're comparing these voltage commands to the measured true voltage, and then you would have inner voltage loop at a minimum. And if you're really rigorous, you could have both an inner current and, or let me see, I guess there would be, this would feed a voltage loop that would feed an innermost current loop. And then you could actually implement current limiting on that innermost current loop. So there's all sorts of advanced implementations you can do that go a bit further. And yeah, you can also generalize this analysis to all sorts of network topologies. And there's a bunch of papers from not only what I've been up to, but also people at other institutions that have been looking at this.
Hey, Brian, I have a question. In terms of implementation, you have shown this implemented everything on the FPGA platform. So there is more from a convenience point of view. Are there any difficulties in relation with the microcontroller kind of hardware?
Yeah, so there's the DC to DC experiment was done with an FPGA. All of the DC to AC experiments have been done with DSPs, C2000, Texas Instruments DSPs. And actually in my lab now, we've pretty much exclusively moved to using C2000 DSPs. We've had great luck using those. I think they're a bit easier to work with than the FPGAs, but you could use either one. Now going to things that are even simpler like microcontrollers or really low cost digital controllers, I personally haven't had experience using those systems, but I imagine that you would just have to make sure that your sampling resolution on your ADCs is sufficient, and standard considerations that you need for most any other controller.
So at what sampling rates you are doing with the C2000 platform?
We're sampling, let me see, I think for most of these systems once every switch cycle.
Okay.
I think you could get away with probably sampling once every couple switch cycles. This controller for at least the DC to AC case is pretty slow compared to the AC waveform. Going back to my other presentation for the DC to DC case, the version I showed you today is kind of, I'll say it's the old one from last year, where, or actually maybe even more than last year, where we had to do a brute force sampling to actually measure the ripple content. As of last year, last summer, 1 year ago, we have a compile paper. We do a sample and hold once every switch cycle in the DC to DC converter, and we can get the same behavior. So anyway, I think for the interleaving case, you need to at least sample once every switch cycle.
Okay, thank you.
Mm-hmm.
Oh, one more question in the chat, Brian.
Okay, so Tauba is asking, what is the motivation behind choosing parallel inverters connected to a load? And can we generalize the network topology to other types of interconnection? Oh yeah, I guess when I glanced up, I was lumping that in with a previous question. Yeah. So this restriction I was looking at with the parallel case across one load is purely artificial. There's no the only reason I did that for my presentation is because I was trying to tell a story that includes both the DC to DC and DC to AC case, and I was looking at these angle configurations. But in general, it doesn't matter. If you're just looking at, let's say, AC systems, microgrids, power systems with these types of controllers, you can look at any network and you can apply whatever analysis you want. So yeah, let's not interpret it, what I showed here as being the only case. If this was just me to tell a very particular story today. Okay, so Priyanka asks, mic controller is used for maintaining AC signal or DC signal or what, sir? Okay, the microcontroller is basically just used as shown in here and my other slides. You're processing measurements, and then the actuation part is the only part that's different. For the DC to AC case for inverters, the actuation is going to the PWM to synthesize the AC waveform itself on the switch terminals. And for the DC to DC case, the actuation of the oscillator is going to synthesize the carrier signal of the PWM. So that's the only difference between the two.
Yeah, please continue, Brian. We'll take questions at the end.
Oh, I'm done. Yeah, I'm just having fun here with questions. Yeah.
Okay. Guys, please unmute yourself and you can go ahead with the question.
I also have a little bit of bonus material here. If there's time, I have a
yes,
video.
please go ahead.
Yeah, I was going to say that I have a little video here that want to, I felt like some of this is stuff that's research moves fast. Things can get dated quickly, and I have all of these new things we've been working on, and I want to show them off a little. So this is the newest version for the DC to AC case, and this is for AC systems, microgrids, and I wanted to show an experiment here that we actually ran in my lab. So let me pull up a video. All right, so this is something I put a fair amount of work in to produce. All right. I'm going to show everyone here a experiment that is meant to illustrate the behavior of these virtual oscillator controllers, the most recent incarnation where we have the P star and the Q star, the set points that bias the droop behavior, and show how this can work in what I'll call infinite inertia, where you're connected to a 100% stiff grid, as well as zero inertia, where if you island the system, it's just its own loads. Okay, here's what you're going to see. On the left-hand side, you're going to see a diagram where this is going to be dynamically changing, and this is going to be showing the measured waveforms in real time. And then you're going to see some characters running around up here who are actually running the experiment. So this is a video. I think it's pretty one of a kind. I haven't seen other people do this where I'm going to show you this experiment. Now the The red and green just tell you whenever the converters are turned on and off. The color codings of these voltages and currents will be shown on the scope. And then I also have these little meters. You'll see this one is showing the frequency of the system. You can tell we're in North America, it's at 60 hertz. So we're going to start the system at turn off, and then we energize the first unit. It's hiding behind an open circuited switch. So the current flowing through it, which is in blue, is 0 amps. And its power command is 0, and it's measured real power is 0. We close the switch, and there's a small amount of reactive power. So its real power is still indeed 0. Now you're going to see here, keep your hand on the upper left. We're about to issue a step change in power. And indeed, the power does go up. So now this thing is injecting power. It's mostly going into the grid and some loads. And then what we're going to do here in a moment is we're going to turn on the second converter. It has a non-zero power command, but it's hiding behind an open circuited switch. And it's drifting along. So you can see it's completely moving around. Now, what Rahul is going to do here is he's looking at the waveforms, and whenever they synchronize, he's going to close the switch. And now you can see they're both injecting the same power command. And the power command and the actual power for both of them are the same. All right, so here's an event where we have a step down in power command in unit number 1. So you can see its power, which is this blue waveform here, goes down. So these things can track real and reactive power commands when you're on a grid that has the exact nominal frequency. Now we island, okay. Now this is where commands and actuals can differ because we just have to satisfy the load no matter what it is, and frequency droop kicks in. So the frequency can drift around a little bit. Now what we're gonna do is converter number 3 is now gonna be turned on. It's hiding behind an open circuited switch yet again. And Minghui is actually looking at the scope. He's just using his eyes. And whenever this is like the whole 2 light bulb trick with machines when you close the switch, he's just looking at the oscilloscope, and when the waveforms align, he closes the switch. And so here they're actually sharing in proportion to their power commands. So units 1 and 3, which are green and blue, are producing the same current. Unit number 2 has a larger power command. All right, so I think next here is just a step up in power unit number 3. So now units 2 and 3, which are this orange and green, provide more current than unit number 1. Now what we're going to do here is we're going to go to a light load condition. So keep an eye on this load. We remove it. And what's amazing here, and let me pause this a moment, is that because we're islanded, we have such a light load, and the sum of the commands is so much larger than the true demand of the load, the power actually will flow in reverse into unit number 1 because it has the lowest power command. So if you had a battery, you could start charging this battery here. And you can see the phase offset. You're dumping power from units 2 and 3 into 1, and that's the remainder of what this load doesn't consume. And then to close out the experiment, we're going to just give them all the same power commands. So we're going to increase, I think, the power command for unit number 1. And now they're all sharing equally this very light load. And that's all. So anyway, that was another little
Brian, what?
Yeah, go ahead. You might have muted yourself. I can't hear what you're saying.
Yeah. I wanted to ask, what do the arrows indicate? P1 star, P2 star?
Oh yeah, this is just a visual representation of the magnitude of what we're commanding and what their actual power is. So if I go to here, that's comparing this value that we're changing this in the watch window of Code Composer Studio.
Okay.
And then the actual P is showing what the size of the true power coming out is, which can be different. Mm-hmm.
So how did you put this thing together? I haven't seen anything like this before. That's why.
Yeah. Oh gosh, yeah, it was a lot of time. So I've gotten really into learning how to use Adobe's software. So Adobe has their Creative Cloud suite.
Yeah, yeah, yeah.
And I use Adobe Illustrator to create this.
Okay,
and I
okay.
forgot it. They have a software that is meant for video editing. So I created a setup where I was updating the image here. This is actually a collection of images,
Yeah, yeah.
one at a time, 30 or 40 of them. And then we grabbed the video from the oscilloscope and recorded that. And then there's I think and then there's Soham he's holding the phone, he's recording it.
Okay,
And
okay.
yeah, it was really like a symphony here. This
Yeah.
is a true performance. It was really fun to get this put together.
Yeah, really. Yeah, this is really well to understand because I haven't seen something like this before. Yeah, really
Yeah.
great.
Yeah, this is one thing that would be cool if papers could have such a thing. I guess they do allow, I think
Yes,
IEEE does
multimedia.
now. Yeah, that would be really neat if people started doing that. I'm considering it. Okay, Tauba has a question. Is there any difference between single phase and three-phase VOC operation? There is some differences. So here, this is the three-phase version where we use this coordinate transformation here to achieve this. We have two variables. With single phase, you would just have the alpha component would come straight from measuring the single phase waveform. The beta component, if you set the beta component to just be 0, you can end up with a little bit of harmonic content on your output, but it will still work. If you're not happy with that harmonic content, you can use like a 90-degree phase shift of the measured value to synthesize the beta component. Or you could use a transfer function that gives you a 90-degree phase shift of the alpha component to give you the beta value. And that will reduce the amount of harmonic content that you see propagating to your control output. But both will work.
Yeah, if there are any other questions, please unmute yourself and ask. Yeah.
All right, how many bits the microcontroller? I think most of these experiments here we're using single precision floating point values for all the internal signals that's 16 bits is single precision. The analog to digital converters are 12 bits on the C2000s that we're using. In our future experiments, we're building more advanced hardware where we're migrating towards the most advanced and latest DSP that TI has just come out with. That one has a double precision floating point, so it'll be 32-bit for future experiments. I think the ADCs are still 12-bit, so that's where we're going.
Good, Brian, because I have seen many people use only D-space. Good that you are building something from ground up. Very rare to see.
Yeah, D-space, it feels like you're playing in Simulink from what I've heard. I've never used it before. It's very convenient.
So,
but
it's an overkill, actually. Just if you are just producing PWM pulses, D-space is an overkill. Yeah. Guys, we have time for a couple of more questions. Just unmute yourself and go ahead. Okay. And I had one question, Brian. What is the power level of the converter? The one you showed at the beginning? 5 converters?
Oh, yeah. So there's a variety of things because these results have been collected over, at least 5, 6, 7 years. So these most recent ones that are in this experiment, these are 1 kilowatt converters. Going to these other slides here, If we go to, let's see, the DC to AC case.
And all are silicon switches, right?
Yeah, silicon switches. These are 1 kilowatt. Actually, some of these waveforms here, these were for really tiny baby size converters. I think these were maybe like a couple hundred watts. These were the very first experiments I did here.
Got it, got it.
This experiment is on the 1 kilowatt unit. And I think the DC to DC converters, I forget the power rating, is probably around a few hundred watts.
Okay, okay, okay. Got it.
And what is the switching frequency in all these converters?
I think for the DC to DC case, this was, oh gosh, probably something in the 25, 50 kilohertz. So it's a pretty low switching frequency. And that's due to the fact that this old implementation, we had to do the brute force sampling. We've solved that problem now, so we can move to higher switching frequencies with the most recent results. For the DC to DC case, the DC to AC case, I believe this 1 kilowatt unit was switching at 50 kilohertz, and same even with the other slides I showed. Yeah.
Do you foresee some issues or some concerns when we bring down the switching frequency, or the control works just the same?
No, I think the control works pretty much the same. So yeah, I don't foresee major issues with that. The switching frequency is not much of an issue.
Okay. Like in the conventional control, we talk about the bandwidth being at least a decade below the switching frequency, and that in turn results in your responses, transient responses. So you see such kind of equivalent limitations in this particular control method?
I think what you're hinting at is more important to the earlier question about so Pankaj was asking about these intercurrent and voltage controllers and stuff like that. That's where you really need to be careful with bandwidth, because those are operating. You can think about this structure as having a timescale separation. So if you had this controller and there was inner loops that were inside of here, this oscillator actually would be something that's dictating AC waveform level dynamics. So you can say, millisecond or sub-millisecond dynamics governed here. Maybe your voltage loop would be maybe 1 order of magnitude faster than the oscillator, and then your current loop would be the fastest. It could be, a couple of order magnitudes faster than the oscillator.
Okay. Thank you.
Okay.
Hello.
Yeah, go ahead.
Hello, Brian, and we are grateful for the time and effort you took to share your knowledge and experience. I would like to ask you regarding on DC-AC modular structures. It's shown me that it would be for a single phase. If I want to extend it for the 3-phase, it will have some issue.
Oh, no, actually, and this is what Tauba was asking about. You can actually use this for both single phase and 3-phase. So this is the most new version of the oscillator controller for DC to AC systems. And in fact, it works most beautifully for 3-phase. So we measure 3-phase waveforms. We use a stationary reference frame transformation to grab orthogonal alpha beta components. So this is a 3-phase controller most naturally. And I was trying to give some details to Tauba's earlier question of how you can also use the same controller for single phase. For single phase, you would just, the waveform coming out that you measure would just be your alpha component. You would have to synthesize the beta component with a transfer function or a delay or something like that. But then you can recycle the same thing.
Okay, that's fine. Thank you.
Yeah, and Brian, I think control is usually simpler for 3-phase, right, compared to single phase.
Yeah, if I had to pick, I like 3-phase a lot more.
Yeah.
It works better, but if you really want a challenge, you can always look at single phase, but it works there too.
Got it. Okay, I don't think there are any more questions. Thank you, Brian. Thank you for your time. It was really, I had not seen videos like that, and also the explanation was very, very good. Thank you for your time. Thank you for waking up early to give this presentation. We greatly appreciate it. And IEEE PELS and IES Society is very grateful for your time. And thank you, participants, for your questions. I think we will end the meeting now. Vishal, you can end the meeting. Thank you.
Great.
Thanks,
Well,
everyone.
thank you for the
Thanks, Brian.
invitation. And just to close out, I'll just tell those of you that invited me, I'm happy to have a follow-up conversation. You know, if I were there in person, we would be having a cup of coffee or tea after all this and getting to know each other. And I'm interested in doing that. So just shoot me an email and we can have a conversation later in the week.
Thank you,
Yes,
Brian.
yes.
Yeah. Thanks a lot.
Thanks, everybody.
Thank you.
Bye-bye.
Yeah.
Thank
bye.
you.
Yeah.